Thank you very much for coming, despite the alert of the weather conditions. But I hope you might enjoy something. So here is the title of my talk, Early Universe Cosmology. I'm going to try to give you a guided tour in early universe cosmology. And to do that, I need, first of all, to just tell you what is the cosmology. So cosmology is the study of the universe as a whole. And our universe is very old and is very large. It's very big. What do I mean by that? The universe is about 13.8 billion years old. And if you would like to have an idea what does this mean, the Earth is 4.5 billion years, the Sun is 5 billion years, and all the stars that we can see are about 13 billion years. And the universe is very big. The most distant objects that we can see are about 10, let's say 16 times 10 to the 23 kilometers away, which means that it takes about 30 billion years for light to cover the whole size of the universe. Light travels at about 300,000 kilometers per second, which means that in 1 year it travels about 10 trillion kilometers. And just to give you an idea, the Sun is about 8 light minutes away from the Earth. So let us dream that here we are in your beautiful city, and we just walk around the old city, we see up in the sky, we're amazed by the beauty, the mystery, the harmony that exists there. And we might be tempted to start asking some questions. Why this? Like, how was created the universe? What is the universe made of? How does the universe evolve? What is the ultimate fate of the universe? This is the questions that probably you might wonder. In order to be able to answer these questions, we need Einstein's theory of general relativity and very precise measurements which we have with the tools of our 21st century. So if you are looking up at the sky, provided the sky is clear and all that, you see the Milky Way. This is the center of our galaxy. And then you see that every star, every galaxy, every cluster goes away from each other with a speed which is proportional to their distance. And you might be surprised how come this could be. This almost goes against Newton's law that tells us that every two masses, they are going to be attracted with a force which is proportional to the product of their masses and inversely proportional to the square of their distances. So in order to understand the evolution, the dynamics that govern our universe, we have to go to our old friend Einstein and see the theory that he has developed. So basically, Einstein's theory tells us that when you have a massive object, this is going to curved space-time, and then you have this beautiful kind of landscape of hills and valleys. Now, space-time has some invisible structure which is going to direct the way that we're going to move in the same way that you have the slopes that they are going to take to the skier how to move, or the waves that they will say to the surfer how to move. And we can perceive this invisible structure like the force of gravity. Now, Einstein developed his theory in 1915, and it passed all possible tests. In 2004, NASA launched the GRB mission, which was able to confirm two of the basic kind of predictions of Einstein's theory. The warping of space-time around the gravitational body, for this point was about the Earth, and the amount of space that the spinning body, in that case was the Earth, pulls together as it rotates. Einstein's theory predicts as well the existence of black holes. But in order to tell you what they are black holes, I should tell you a bit. What is the life cycle of a star? You know, the star, once the conditions are appropriate, it burns material in its center. That's why we see it. At some point, it runs out of fuel. It has nothing more to burn, and then it dies. So what we have is, as a matter of fact, that at the beginning you have a star that remains as it is because you have the balance between two forces, one that goes outwards, one that goes inwards. This is what we call, well, doesn't matter, I'm not going to confuse with that. And then at some point, once there is no material anymore to burn, you cannot have nuclear fusion as well. At the center, there is nothing to burn, it dies and becomes a compact object. What it becomes when it's dead depends how massive it is at the moment that it died. So if, for instance, has a mass about 8 to 10 solar masses, when it dies, becomes what we call it a white dwarf. At that point, it has a mass almost like our sun, 1 solar mass, and has a radius which is about 100th the radius of the sun. Our sun, when it's going to die, it will become a white dwarf. If, however, the mass is higher, between 10 and 20 solar masses, then it becomes what we call it a neutron star. It has a mass a bit bigger than our sun and has a radius of about 20 kilometers. This is an extremely compact kind of state. If you take a teaspoon of a neutron star, it's going to weigh like 1 billion tons. The magnetic field is 1 trillion times that of the Earth. The surface gravity is more than 100 billion times more than the one that we have on the Earth. It spins up something like 700 times a second, so 60 million times faster than the Earth. And if, when it dies, it is more massive, then it becomes what we call it a black hole. Nothing can escape, not even light. Now, of course, we studied and we said a lot about black holes, but we were not sure that they exist. And then we had this magnificent kind of instrument, if you wish, the Event Horizon Telescope, which is an international network of radio telescopes which are going to detect radio waves up to about 250 gigahertz. So indeed, the 10th of April of 2019, we had the first images of a supermassive black hole located about 5.4 million light years away from the Earth and having a mass about 6 billion solar masses. A bit later, on the 12th of May of 2022, we had an image of a black hole within our own galaxy, located about 26,000 light years away from the Earth and having 4 million solar masses. So there are black holes there. A year after the development of his theory, Einstein came up with the predictions of the existence of gravitational waves. Gravitational waves are these ripples of space-time that they are caused for some kind of very violent event that they can take place in the universe. They create this kind of waves which they propagate in all directions away from the source in the same way that you have these waves on a lake. And according to Einstein's theory of general relativity, these ripples, they travel at the speed of light and they come to our detectors. And what it is important, they don't interact almost with anything they find in their trajectory. So they give us a unique way of just, understanding where they come from. Now, there was a very long path for the discovery of gravitational waves. There are many people who actually contributed. And here I have a few ones that allow me to just mention a few of them. Let me start with Heaviside in 1893, which actually introduced the gravitational analog of Maxwell's equations. And he showed that they produce waves that they travel at finite velocity. Later on, in 1905, we have Poincaré, who actually assumed that the gravitational force is going to propagate at the speed of light, and then from there he was able to deduce that there will be a lag, a time lag, between any change in gravity and its effect, and he says that this effect is going to be transmitted with onde gravifique, which in French is what it says, gravitational waves. A bit later on, we had Abraham in 1912, who actually is the one who the only theory that he liked is electromagnetism. And he thought that accelerated masses should emit gravitational radiation. A bit later, we have Nordstrom, 1912 to 1913, who came with this amazing, beautiful idea that there is an intimate relation between mass and geometry. And finally, we have Albert Einstein. Now, Einstein was very skeptical about the really existence of gravitational waves, and he was not sure whether really there is kind of pathology of the theory of they really exist. And that put a break in any kind of activity about searching for gravitational waves until Einstein's death in 1955. And then there was this conference which took place in Chapel Hill in 1957, which is called The Role of Gravitation in Physics. And the reality of the existence of gravitational waves was thanks to the work of Bondi, Pirani, Robinson, and Troutman. As a matter of fact, a year before, in 1956, Pirani wrote a paper which he entitled On the Physical Significance of the Riemann Tensor. I think I go very fast here, where he shows that gravitational waves are going to manifest themselves as fluctuating tidal forces on the masses of the objects that they found in their trajectory. That was a fantastic, a brilliant idea, which actually is the basis of the search for gravitational waves. Despite that, it took almost 60 years and hundreds of people, theoreticians, experimentalists, in order to be able to make a direct detection of gravitational waves. The first direct detection of gravitational waves, which was the ultimate test of Einstein's theory of general relativity, was made on the 14th of September in 2015 by the two twin interferometers in the US. They found both of them a signal in their interferometers coming from two black holes that I told you before that they exist in Einstein's theory, which collided 1.3 billion light years away. So what actually happens is that you see the way that this instrument works. You have these two arms that you see there, okay? And you send a light beam that goes along the two arms. The two arms, by construction, they have the same length. So if nothing disturbs this length, then the light that you send and you split it in the two arms, it goes, it comes back, it takes the same time. But if there is a gravitational waves, it stretches space-time, and therefore what it happens is that we are going to have the length to be different, so the time of arrival is different, and that's the way that you can detect that there is a passage of gravitational waves. So what is amazing here is that the gravitational wave power that was radiated was more than 10 times greater than the combined luminosity of every star and every galaxy together in our universe. The gravitational waves that came from this event, they traveled 1.3 billion years. And when they arrived on Earth, they produced an effect 1/1000 of the diameter of the proton. Is smaller than the thickness of the human hair. To me, the most amazing thing is to be able to detect that. By now, we have 100 of detections. We keep going, and we expect, as this current run goes ahead, we will have a few more hundreds, which they open a lot of possibilities in studying astrophysics, high-energy physics at energy scales we cannot reach in any accelerators, nuclear matter, and so on. So even testing GI, if you wish. So now I go back to my questions, okay? How was created the universe? If you go, now that I told you what is Einstein's theory, somehow, okay, if you take Einstein's theory and you run it backwards, your equations in time, you will arrive at a state where you have all the matter and energy that you see today in the universe in one point. What happens there is what we call it the Big Bang. Okay, that's a point from where, if you wish, okay, that's a way of talking, that everything has been created. But then there are extreme conditions of energy and density. And that's where the theory breaks down. We call it a singularity. What does this mean? We have a point that will have infinities, infinite mass, infinite energy. We don't know. We don't have a theory to deal with that. Of course, one might be tempted to ask, how did the universe come into being? What was there before the Big Bang? Is the singularity real? Is this kind of, the point that our theory breaks down? Is some pathology of the theory? Is our theory which is incomplete? And as a matter of fact, there are two fundamental theories in physics: quantum mechanics and general relativity. So if you go to describe the behavior and the position of atoms and subatomic particles, then all the certainties become probabilities. You enter the realm of quantum mechanics. And what happened is that general relativity and quantum mechanics, somehow, they're incompatible. They're like two theories that they have some kind of, of limit when they work, but together they have to find a more general theory to accommodate them. So there are this kind of attempts, people to try to put together quantum mechanics and general relativity. Okay. So there are several probabilities. Probably many of you watches this kind of Big Bang theory, okay? And you have seen that there is this guy Sheldon, which goes around thinking that is string theory. What does it say? If you see closer, you have a loop, and you see closer the particles, then they are not points, they are like strings, open or closed. So you have many vibrations of the strings, and they create all the particles. Then you can have these kind of strings that they chop off, they intercommute, they split, and they create the interactions. And you might have another kind of, there are many other approaches, let me highlight one of them, which says actually, which is here Leslie, which goes with what she calls loop quantum gravity. So instead of having the strings, you have one-dimensional loops. The space you cannot split it into smaller and smaller and smaller pieces. At some point, you hit the granularity of your space, okay? It's not continuous, it is discrete. You have the space formed out of quanta of space. Now, of course, you might say, how can you test such a theory? Okay, can we test it? For the time being, any of these theories could be partly correct, completely correct, or completely wrong. To accept such a theory, it doesn't have only to be consistent per se, okay, by itself. It should describe the universe in which we live. So nature is going to tell us. So if you go to take early universe cosmology, you might be able to see which is the correct theory of putting together quantum mechanics and general relativity, which you need to describe the interior of black holes or the Big Bang, and somehow unweave the fabric of the universe. Of course, you might be tempted to go and ask again, what came before the Big Bang? That will give us some idea about the birth of our own universe. Now, we cannot experience this phase, but I think it's worth to try to create the mathematical tools, the theories, in order to be able somehow to unravel the mysteries of the universe. And now I go to my second question. How does the universe evolve? So we have what I told you before, the Hubble's law. Everything goes away from each other with a velocity which is proportional to its distance. So if you see things, if it's like if you are living in the surface of the balloon, okay? Then you blow the balloon, it becomes bigger. This does not mean that galaxies are moving through the space. The only thing that means is that space expands. As it expands, it carries these galaxies or clusters or whatever you want together. And then we know from the data we have today, I will come to that later, that what we call it, the spatial curvature is flat. What do I mean by that? You should not consider that this means that I have a flat pancake. No, it's not that. It means that I can use Euclidean geometry. It means that if I want to find the distance between you and I can use the Pythagorean theorem. That's all it means. So the next question is, what is the universe made of? Okay? So the universe is made out of stars, of hot or cold gas, but mainly it's made out of something we don't know, that we call it dark matter. I tell you why we need it, and something which, again, we don't know, and it's called dark energy, which is even more mysterious. So we found ourselves in the rather embarrassing situations to say, well, here we are, we don't know about 96% of the content of the universe. So why do we say that we have this dark matter? Consider some galaxies. Here, I give you some nice pictures. So there are about 60,000 light years across, and they contain about 10 billion stars. Fine. Then I have the clusters of galaxies, hundreds to thousands of galaxies. And you see that they are bound together. To be bound together, they need some mass. Otherwise, they cannot be bound together. Newtonian's law. But what we see, if we go to find out how much mass they have, by going to study how much light they give, then we are stuck. They don't have enough mass to be bound. So something is here. That's what we call the issue of dark matter. Okay, so we know that dark matter exists. It should exist. Clusters are mostly made out of dark matter. This was said from Zwicky in ages ago. Embarrassing to tell you how many ages, because still we don't know. And if you go to measure how far the galaxies go, as you go away from the center of a cluster, if there is no mass, by taking Newtonian's law, then the velocity should go down. But it's not. It remains constant. That there is something there that has gravitational interaction, but no light. So that's what we call the dark matter. And the issue of dark matter is quite old, and yet, despite many experimental attempts, it remains unresolved. Dark energy, even more mysterious. The universe is expanding with an accelerated expansion, okay? So the speeding up of the expansion of the universe is at a rate which we cannot explain. So there is some kind of conflict between our data and our theory. So this accelerated expansion of the universe could be explained through the existence of something hypothetical that we call it dark energy, and we don't know what it is. And our universe should have entered this kind of period about roughly 5 billion years ago. So we need something in order to explain the data we have. So the theory which is based in Einstein theory that discusses this kind of evolution of the theory is what we call the Big Bang theory. So, model whatever you want. It's very dangerous to start calling things theories. They're more of a models. Anyway, it describes the universe from its first formation fraction of seconds up to now. So what it tells us is that at first we have a primordial soup of subatomic elements which interact with light. As the temperature of the universe drops, you have a particular kind of values that at that point you can allow for the formation of protons, neutrons, and a bit later of nuclei of hydrogen and helium. The first stars, if you wish. After about 300,000 years, the matter decouples from the photons, so now the universe becomes transparent. At that point, our universe is made basically 75% of hydrogen and 25% of helium. Hundreds of millions of years later, the universe enters what we call it the reionization phase. And in the last era, which is about 13 billion years, the stars and the galaxies were formed and evolved. So the universe has started from a state of gas which was quasi-homogeneous, okay, to a rather inhomogeneous distribution of matter. That's why you have clusters of galaxies in the void next to that. And you have these filaments of matter that you can see in this kind of beautiful, I think, is a numerical simulation kind of production. And there was a very precise kind of detection, if you wish, that came by luck, which confirmed this Big Bang theory, is the cosmic microwave background. These are the relic photons from the Big Bang that came to our antennas. That was discovered by accident, by chance, by two radio astronomers, Penzias and Wilson, in 1965, which they saw this kind of electromagnetic spectrum coming from everywhere. So it could not be a noise, it should be something more intrinsic, okay? And this is, because it has a thermal spectrum, is the most solid kind of evidence that the universe has started with a hot phase. Now, this kind of, today our universe is cold, because the expansion of the universe makes the temperature go down. Today the temperature is about 2.7 degrees Kelvin, and somewhere is hotter, somewhere is colder, that you see the blue and red spots, and there's more discrepancies, so it's almost the same with small fluctuations of about 10 to the minus 5, and that will pose another problem. The geometry of the universe, I told you before, to map this data with the geometry that we have been found is what I told you, this flat. Remember what flat means here? And that will tell us as well that the universe, it will keep expanding, the fate of the universe. We are in this green curve, that means that the universe keeps expanding. If we were in a closed, then the universe was going to go from a big bang to a big crunch. This is not the case. So there are some limitations, however, of this Big Bang theory. It's extremely successful. The light elements that we see of the universe, this microwave background, it's a big success. But despite that, there are as well some kind of problems. One of the problems is the fact that the universe is with a very high degree flat today. Flat, keeping in mind that the distance between two objects can be calculated with the Pythagorean theorem. That's what I mean by flat. And we know that this flatness should somehow increase with time. So if today is very much flat, it should have been much more in the past. It's a particular initial condition. And we don't like particular initial conditions, as a matter of fact. We try to explain. The second is this horizon problem. I told you before that there are small fluctuations in the temperature, okay? But we see places in the sky very far from each other, which, according to Einstein's theory, light could not be from here there, and they have the same kind of difference in the temperature. How could be this possible? This is a particular initial condition. Unless you take account of anthropic principle, which we don't very much like, then you have to be stuck that something probably has to be done. And then it was suggested that there is this cosmological inflation. This is something that solved to some extent, I'm not going to go to a big discussion about that, the nightmare of people about the hot Big Bang model. Is not going to solve any kind of nightmare about financial issues, I'm afraid. But anyway, that was the point there. What it says is a very fast kind of expansion, very fast. So the points that we see, the regions of the sky that we see today, they came from the same initial region. So they had the same initial conditions. So if you would like, what you can see here is that inflation increased the size of the universe by a factor of at least 10 to the 26, which means 26 orders of magnitude between 10 to the minus 36 and 10 to the minus 33, 0.36 zeros, 1 after the Big Bang. So that's the model that says there. So the interplay of general relativity, of astrophysics, of particle physics, with the use of very precise measurements and observations, help us to understand our universe, its laws, and its evolution. And here I give you, for instance, the SKA, the Planck, these are buzzwords, if you heard, the Euclid, LIGO, Virgo, Kagra, Einstein Horizon Telescope, LISA in the future, ET in the future, some experiments for dark matter, and the LHC collider in Geneva. However, despite the fact that we live in a golden era for cosmology, there remain some open questions. That's why we're here, as a matter of fact, and further kind of progress needs to be made. We have to understand what gave this the very early expansion of the universe. We have to understand what gave this late accelerated expansion, what gave this buzz of inflation and dark energy. We have to understand what makes a cluster of galaxies to be bound, the dark matter. So, and of course, we need, at the end, to find a theory that will make these old friends, Planck and Einstein, quantum mechanics and general relativity, to be happily together. Sorry. So, as I said before, even though we cannot experience the phase leading to the birth of our universe, we try to construct the mathematical tools that will help us to unravel its features. And allow me to say that this is the beauty of theoretical physics. Thank you very much. I will not try to say that in Polish.